Hello, everyone, and welcome. So this is the first lecture of a little series whose aim is to introduce geometric group theory. The main theme of these lectures will be quasi-isometry invariants. But first, I would like to start with explaining a little bit what is geometric group theory about. So geometric group theory So what we're trying to do is to analyze the algebraic properties of groups using geometric methods. Okay? And so typically, how do we do that? Well, we consider group action. So this leads us to consider group actions by isometries on metric spaces. Okay, so let me be a little more precise. So X D will be a metric space. Okay, and we will consider the group of isometries of X. So these are the maps G from X to X that preserve the distance, meaning that for any points xy in X, if I look at the distance of the images of 2 points X and Y by G, then it is the same as the distance of X to Y. Okay, so looking at a group action means that we are looking at a group G at a morphism phi to the group of isometries of X, where phi is a group morphism. Okay, so what sort of questions do we want to answer? So first, so these are very general questions. Which groups act on which space? Okay. Second kind of general question that we have is if there is if a group acts on a space, what can we say about the group and what can we say about the space? Group act on a space. What can be said about the group and about the space? And the last question that I would like to stress is the following. If we see a group as a metric space, how does it look like? So these are the principal questions leading the theory. So maybe before getting before what I would like to do now is to give you a sample of what it means, what kind of results we can look at. And so the proposition I would like to prove, so that illustrates a little bit all this framework, that is relatively simple, is the following. So the following proposition. So we assume that a group G, let G act by isometries on the Euclidean space Rn, where I assume that n is at least 1, if the action is free, then the group has no torsion. So maybe I should explain or remind you what does it mean to have a free action. So a free action means that if given an element G of my group, there exists a point x in Rn such that G of x is equal to x, then this means that G acts like the identity mapping. Okay? So this means that the action is free. And what does it mean to have no torsion? So it means that to have no torsion means that if for every element G that is not the identity, the neutral element, and for any positive power, it is different from the neutral element. So no powers of a non-trivial element is trivial. Okay, so what does this proposition says? So I assume that I have a group acting on the Euclidean space. I have a property on, so the geometric properties is the fact that I have an action on Euclidean space by isometries, and I know that the action is free, and the conclusion is an algebraic statement saying that the group has no torsion, meaning that for no element, it is equal to the identity. So let me sketch the proof. Okay, so I assume I let G an element of the group. So you see, maybe I should say that I'm looking at an action of an abstract group by isometries, but this means that I have this morphism. So each time I never think about the morphism being explicitly stated. I see G already as a subgroup of the group of isometries, even though the map might not be one-to-one. And so I assume that I have an element G, and that I have this element has finite order. So this means that there is an iterate M, or at least one, such that the mth iterate of G, so let me just remind you that this is G composed with itself m times, is equal to the identity map. Okay, and I want to prove that actually G is already the identity map. Okay? So how are we going to do that? For this, you pick a point x in Rn, and I will consider its orbit under the element G. So I let O to be the set x, G of x, and then I take the images of the images. So the second iterator of G, so I apply G to G of x, G2 of x, then I arrive at G minus 1 of x. And then if I iterate once more, since the map is the identity, I go back to x. And so the sequence of iterates of G applied to x is a finite set. Okay? So what's the picture? I have a finite number of points corresponding to the orbital. And so the only property that I have is that the group acts freely. So somehow what I want to do is to show that there is a fixed point, that G admits a fixed point. So how will we do that? So the thing is, this looks a little like a grid, and it should not. So I will add some points a little everywhere. So the geometric property that I will use from Euclidean space is that I can find a ball containing my orbit of minimal radius, and this ball is unique. So there exists a unique ball of minimal radius containing my set O, because O is a bounded set, actually. Okay, so maybe I should erase my board. Okay, so let me just comment on this result. So first, the fact that there exists a ball of minimal radius, this is not very hard to prove in Euclidean space, because you know that balls are continuous. It's just an idea of controlling the center and the radii. The centers and the radii of the balls, and then by a compactness argument, you can prove that there is a ball of minimal radius that contains the set. And now that it is unique, it's because if you had a second ball joining the two, like for instance something like that, let's say that it is of same radius, so this is ugly, I'm sorry. Then what you see is that there would be a smaller ball, because here what you can see is that maybe the drawing is not very good, so I'll do it here. So let's assume I'll do it that way. I have a first ball and a second one, the same radius that intersect the same set. So my set O is somewhere in the middle. And then what I claim is that then there would be a third ball of radius strictly smaller than that. Okay, so this explains why I can find such a ball and that it has minimal radius. And also, now what do we do? Well, I have my group G, so my element G, so I let it act, I compute the image of O. So what is it? So I take the image of each point, so it's G of x, G2 of x, and here I arrive at Gm of x, which is equal to x. Okay, so this is O. And then my ball, my minimal ball, I call it B. So B is a ball centered at some point W and for some radius little r. And so because this ball, the group acts by isometries, the image of a ball is a ball of the same radius. So here it will be a ball centered at G of W of the same radius r. What do we know? We know that since O was in a subset of the ball of B, the image should be a subset of this ball. And moreover, so what we get is that actually O has to be included in the ball centered at the image of W. This implies that O is a subset of the ball centered at G of W of radius r. And now the thing is that R is the minimal radius that contains the set O. And what I just explained is that it was unique. And so this means that this ball has to be the same as the initial ball. And so this means that W is fixed by the element of G. And now, because I know the action is free, this implies, by free action, that G is the identity map. And this concludes the proof. So I started from the fact that I had some power of an element G that was equal to M, and then using the properties of the geometric properties of the Euclidean space, I got to the fact that this element had to be the identity map. Okay? And so this is the kind of game that we're trying to do with geometric group theory. Okay, so now what I would like to do is try to introduce the main objects that we'll study today during these lectures. So these are finitely generated groups. So we say that a group G is finitely generated if a group G, if there exists a finite subset S in G, such that for any element G can be written as a product of elements of S. G, there exists some n and some elements S1, Sn in S, so that G can be written as the product of all the elements. So here I have included the case n equals to 0, because if it is a neutral element, then we won't need any S. And sometimes people say that we can put some power here, epsilon 1, epsilon 2, which is plus epsilon n, where epsilon j is plus or minus 1, depending on if we are taking the inverse or not. So this is just a matter of convention. Usually, I prefer to think of S as a symmetric set, meaning that it contains also the inverses, but it is not compulsory. It depends on the conventions that people use. Okay, so and we will focus on those groups, and also what will be interesting in our case is to think that they are infinite. Okay, so before, sorry, getting forward, I would like to present a family of groups that plays a very important role in this theory. These are the so-called free groups. Okay, so maybe example. Okay, so how do we define those groups if you've never seen them? So you let A be a set called the alphabet. Okay, so from A, so this is a set like A equals, so it can be finite or it can be infinite, but it has to be non-empty at least. And then we formed formally the inverse set. So these are elements that I will write with the same letters. So these are the same elements, but I add a power -1 to them. So this is very formal. And then we consider the set of words that we can make out of the alphabet. The set of words. So these are all the tuples that you can get using the alphabet or the inverse. Okay, with a convention that the 0th power is the empty set, or the empty is made of the empty word. Okay. So now I want to build a group out of the set of words. So I need a law for that. This one I've already used. And the law will be given by the concatenation of words. Okay, so maybe let me just make a small comment here. So usually an element here, so it means that we are looking at elements of the form AJ1, AJ2, AJK, okay, where you can have maybe some powers plus or -1. So the tradition is not to write the words like this, but to forget about the brackets and seeing it really like a genuine word. So it would be written A epsilon1, AJ2 epsilon2, AJN epsilon n. Okay, sorry. Okay, so for instance, an example of a word, it could be A1 squared times A2 minus 1, A4 minus 2, and A5, and maybe A3. Okay, okay, so what we look at, the law we define following law. Given two words, W1, W2, we define the product, W1 times W2, to be the word where we concatenate W1 and W2 together. Okay, so this is concatenation. Concatenation of words. Okay, so for example, if W1 is equal to A1, A2, A1 minus inverse, and W2 is equal to A1, A2 squared, A3, then W1 times W2 will be A1, A2, A minus 1, A1 inverse times A1, A2 squared, A3, that we see as a single word. Okay, so here we obtain a semi-group, but it's not a group yet, because we have a neutral element, and this is the empty word. But otherwise, we don't have any inverse. You see, because each time, if you take two different ways, you only increase their length. So to do that, we consider the equivalence relation generated by, so it's equivalence relation on the set of words, saying that, I will say that W1 A minus 1 W2 will be equivalent to W1 W2. So this means that each time I see a letter, so W1, W2 are two words. A is a letter in my alphabet. So what we do is that each time we see one letter and its inverse, and this is the same if I inverse the two, W1, A minus 1, A, W. Okay. And so this equivalence relation, what does it say? It says that we can cancel letters once we see them both together, one positive and one negative. Okay. And in this sense, if you have a word, then what do I want to say now? I want to define, so the definition of the free group. The free group over A is the set of words up to this equivalence relation with the same law concatenation. Okay. And so, for instance, if you have a word W, which is equal to A1, A2, A3 squared, then the inverse will be, you have to switch everything backwards, A3 minus A3 to the power minus 2, A2 inverse, so maybe I should have put one inverse here so that this is positive. And here I have A1 inverse, because when you make the computation of the product between the two, what you obtain is A1, the inverse of A2, A3 squared, times A3 to the power minus 2, A2, A1 to the power minus 1. And so what you see is that these two cancel. Then, because I have exactly the same number, the same powers, but they are inverse one of the other, here the same, A2 inverse cancels with A2. And then A1 and A1 cancel also, and so what we obtain is the empty word. So what I just showed by an example is that now we know that every element has an inverse, and I don't prove the associativity, which comes for free. So why? So you'll see that these groups are very important. So the first reason for that is that any finitely generated group comes as the image by a morphism of a free group. Okay, so this is some sort of exercise. So maybe first a definition before that I forgot. So I write it down here. I will say that a word is reduced if there are no cancellation. Okay, so the exercise will first prove that FA is indeed a group. Check. FA is indeed a group. And two, that every word admits a unique reduced representative. Okay, so now one motivation for looking at these groups, why they are so important. So there are several reasons, but at least just to go back to finitely generated groups, if S is a finite generating set of a group G, then we can consider a map phi from the free group made up of S with alphabet S into G, where to an element, to a word S1 Sk, we associate the element in G, which is the product of these elements seen in the group. So S1 times S2 times S3 up to Sk. Okay? And therefore, by the universal property of groups, what we obtain is that G will be isomorphic to the quotient of the free group by the kernel of my morphism. Okay? So any finitely generated group can be seen as a quotient of a free group. And so this is important. So now what I would like to do is to explain how we can look at a finitely generated group as a metric space. So, finitely generated groups as metric space. Okay, so for this, fix a group G and a finite generating set. So I assume that S is symmetric, meaning that it is equal. Each time you have an element, you also have its inverse inside. Okay, and so what I will define is the word metric first. So given an element G in G, I let the norm of G with respect to S is the minimal number of elements in S such that G is a product S1 Sk. Okay? And then the word metric is defined for two elements G1, G2. So with respect to my generating set S, it's defined as the norm of, so I have to do it the right way, G2 inverse times G1. Okay. And then, so now, so exercise. Check that GDS is a metric space, and that the action of G by left translations on itself is by isometry. Okay, so what do I mean by that? Yes, explain what does it mean to, so I consider, so if I have two elements of the group X and Y in G, then I associate and G, so here I see it as 2 points in my metric space, and then I look at this element G like an element acting on the group, and so I want to prove that the image G with respect to this metric of Gx, Gy is equal to dxy. Okay, because if I make the translation on the left, it means just that I multiply by G on the left of the elements of the group. And so, of course, in this way, it looks a little abstract. So we have a geometric realization of this of the word metric, and this is what we call Cayley graphs. Of GS. So a graph is given by a set of vertices, V, and a set of edges, E. So E is a subset of V times V. In all the lectures, I think there will be no loops. Okay, so here, how do I define the Cayley graph? So for G, for the set of vertices, it will be the whole group, G, and I will put an edge between two elements if they differ on the right by an element of my generating set. Okay. And so let me give an example of that. So for instance, the simplest example is the set of integers. So I assume that I have like a generator plus and minus 1. Okay, so the vertex set is the set of integers. So I write them this. So here you have 0, 1, 2, 3, etc. Minus 1, minus 2, minus 3. Okay, and now I put an edge between one element G, like for instance 1, and the next one where I multiply on the right by 1. So here, because it's an abelian group, multiplying means that just that I add plus or minus 1. So from 1 I can go to 2 or to 0. And then what you see is that what you are reconstructing is the real line. Okay, but I could have taken another set generating set. So for instance, I'll change colors for that. If I take S to be plus or minus 2, plus or minus 3, then from 0 I can go to 2 or to 3, and go also to minus 2 and to minus 3. From 1, but I cannot go to 1 in one step. So from 1 I can go to 3 or to 4 and to minus 1, minus 2, and you continue like that infinitely. So now let's look at some other example. So for instance, if I take Z2 with the set of generators 1, 0, 0, 1. So in this case, we obtain, just as before, the grid on the plane Okay, so here you have the origin 0, 0. Here you have 1, 0, 0, 1, 1, 1, and so on. And maybe I should give an example with show what's going on with the free group. Last example. So G, it will be the free group on two letters A and B. Okay, so first you start with the empty word. Then you multiply if you have 1 point or its inverse. So if you multiply by A, you get A here. By A minus 1, you get A minus 1. Then you have B and B inverse. Okay, now what goes on? So I can multiply on the right A by A, for instance. So then I get A2, A squared. I can multiply by B. So here I get AB. And multiply by the inverse, AB minus 1. And I could multiply by the inverse of A. But in that case, I go back to the origin, so I forget it. And then I can continue. So each time I multiply by A, then I get a real line exactly like the cyclic group Z. If I multiply by B, then I will get a real line, and by the inverse similarly. And so just to make the story a little short, what you obtain is a tree where each vertex has 4 points. Okay. So it looks something like that. So if I make each edge of the same size, then we won't see anything because it will be a mess. So I just do it like that. And so before I conclude this lecture, I would just like to say two things. So once we define the Cayley graph, so let X be the Cayley graph of a group G with a finite generating set S. Then we can define a metric on X by letting each edge be isometric to the segment 0, 1. So this means that each time you go through an edge, you go 1 ahead. And so the distance between 2 points will be the smallest length of a curve joining them. Okay, and the property is that, so this defines a length metric dx on X. And the thing is that for any vertices G, G prime in G, what you have is that the distance between them is exactly the word distance. We realize the word distance like a geometric distance by looking at length of curves in the graph. And what can we say about the action? Well, if I take the quotient of the Cayley graph by G, so every element, every vertex comes from the neutral element. So this means that I have only one orbit of vertices. So it will be a point. And then for each generator and their inverse, I will have a loop. Okay. So we have a compact set. Okay, so this is S1, S2, Sk. Okay, so for now, I will stop here. And so what we'll do in the next session is to understand how we can look at Cayley graphs and how much they depend on each other when we change generating sets. So thank you for your attention.